Hello. Alright, let's begin. Let me see if I can... Ooh, nice. Okay. Let me pull up the YouTube stream. Okay, let's do it. What was I going to do? I forget. Help me. I was going to begin the lecture. Yes. So let's pull this up. Okay. Here we are. So, let's do some announcements. I went to a Boy Scout camp once. Every time someone said announcements, you had to say, "A terrible way to die." But if you're a Klingon, it is a good day to die. Contradiction. Okay. So, what are the real announcements? Project 3 is due today. So I'll be around until, say 8 p.m., maybe. On and off. To help. Yep. That's all I have to say about that. So get it done if you haven't got it done. And if you haven't got it done, then we'll talk. So let's contract this proof. There we go. What else? The exams. So I haven't started grading yet. I think I'll probably try to get them done by Thursday. So let's reset timetable expectations to Thursday. Oh yes, I like my shirt. It is nice. Well, I'll talk about that for just a second. So, and I was trying to work on that, but I wasn't very good at it. The idea here is that if you want to test your efficiency for your algorithm, what you can do is you can say, if it takes, say, let's say that you create 1,000 random patients, and it takes, I don't know, let's say 0.045 seconds to insert them, and then create 10,000 random patients, and let's say that it takes, well, what is n log n? So it'd probably be something like 0.65 seconds to insert them. Create 100,000 random patients, and it should take just a little bit more than 10 times. So it should be like 8.2 seconds to insert them. And basically, what's happening here is if you do 0.65 divided by 0.45, what you should see is basically something slightly larger than 10. In fact, it could possibly be something like, let's just take the log base. So remember that so if we take the log base 2 of 10, so 10 log divided by 2 log, it could even be up to like 33. It could actually be something like 30, because the log base 2 of 10 is equal to 3.32. And so if you take the ratio right? 10 times the log base log of 10, you'll get about 33.2. So that should be, so for every time that you multiply the number of patients by 10, you should expect the runtime should increase about a factor of 33.2. But of course, this is like the upper bound of runtime increase. It should be probably a little bit less than that. So, but anyway, yeah, that's kind of what you're looking for. So maybe these numbers are a bit off. I'm just giving them as an example. So basically, why would you get a Stack Overflow? It's possible that you're hitting a recursion thing, and it would have insert the same patient that number of times. Inserting the same patient that number of times. I guess for a skew heap, it doesn't. For insert, it doesn't matter. I guess for skew heap. It's going to create a perfectly balanced tree of some kind. So basically, this is the idea here. This is how you would kind of test your efficiency. Yep. All right. I think that's all I have to say about that. Other than the fact that I actually tried to do this and I was getting some weird issues making the patients, so I never even got to test my runtime efficiency. So maybe I'll finish that up today if I have any time. But of course, you know, I'm going to admit that, like, whenever I say, oh, if I have time, I'll just do this, that means I will never do this. So, you know, if it's like, if time, then do X. The problem is that time is just equal to false. So it ain't gonna happen. At least that's like 99% of the time in my life right now. So, okay. Yeah, so the more important thing is that I will try to get your exams back to you by Thursday. I skimmed through about 2 or 3 of them. They look decent, so I'm not expecting the grades to be really bad or anything, hopefully. Yeah. Okay. So just focus on doing well on the project. All right. I guess maybe if I could get them done overnight by tomorrow, because technically the drop date is tomorrow, but I don't think it's going to be a make it or break it decision for anyone. Okay. So let's talk about hash tables. Okay, so what is a hash table? Basically, a hash table is a structure. It's basically, it's a fancy array, is what it really is. And so let me explain to you what I mean by that. Basically, whenever you have an array, right, you'll access the elements by their index. So for instance, if you say, I have an array int pointer array equals new int 1000, and I want to access array 17, I just plug in array 17. And I set that to be 32 for some reason. Or array 512, I'll set that to 512. Or, array 33 is equal to 44, right? So this is how you access elements of an array. And so the only difference between an array and a hash table is that we have a special function called the hash function. And now we're going to leave the hash function mysterious, but what we do is this is how we get into our new array. So if we still have 1,000 elements in an array, what we do instead is we say hash of x is, so the array value of hash of x mod 1000 is now equal to the value. And this is how we insert into a hash table. Okay? So the idea here is that what you're going to do is you're given some kind of hash function, and so your first question should be, okay, well, so what the heck is a hash function? And so the answer is, it's a function that kind of, well, so it takes keys and it produces hashed numbers. And so the idea of it is that so the keys can be integers sometimes, or sometimes they can be strings, or they can be characters, or they can be technically even floats if you're crazy. So the idea here is that a hash function basically eats a key, and so generally imagine that x is a string, for at least, you know, for our imagination purposes. Okay, and so a lot of times the reason why we use strings is because we want to store things, for instance, under like a name or something like that, and so you can't really just do something like array of Eric, you know, is equal to 44, and so you have to do array of hash of Eric, right? Mod 1000, which is the length of our array, is equal to 44. So this mod 1000 is a pretty standard thing because the hash function usually produces numbers that are kind of uniformly distributed, and then what we do is we take it, mod the hash table size. So this is always mod hash size. Okay? All right. So let's do some examples. Let's do an example where we actually use integers. Let's do a simple example. Let's something like, let's make a little hash table. Here is a hash table, right? It's an array for, I don't know, I guess it's 5, 6, 7. Okay. So this is 1, 2, 3, 4, 5, 6, 7. Let's leave it at 7. So now let's say that our hash function, say we're going to be inserting integer keys and integer values. Well, let's insert string values. So let me show you what that looks like. So basically here, the keys are going to be integers. So let me define my hash function. Hash of x is going to be 3 times x plus 5, right? And then we're going to have to take that, so the real hash function of x is going to be, you know, 3x plus 5. I guess we can put parentheses on it just to be safe. Mod 7, right? Which is the total size of the hash table. Okay, so let's insert some values into this hash table. Let's say that we're going to insert the key value pair. So basically, remember that things come in key value pairs. And so let me insert, say, 3 and Eric, right? That's what we want to insert. So how do we insert that? Well, first we have to hash the key. So let's hash the key. So 3 times 3 is 9, plus 5 is 14. Mod 7 is 0. So basically what we do is we say 3 times 3 plus 5 mod 7 is equal to 0. And so then what we do here is we say, since that's the case, we stick this thing in the 0 slot right here. That's where it goes. Okay? All right, so let's do another element. Let's say we hash 17 And let's pick a nice name. Atia. And so where does Atia go? And so the thing is that that name is just the value. 17 is the key. So what we're going to do is we're going to calculate 3 times 17 plus 5 mod 7. And what does that equal to? Well, let's think. So 3 times 17 is 60 minus 9, so that's 51. Plus 5, so 56 mod 7. So what is 56 mod 7? Good question. $56. Oh, that's 45. 56 mod 7 is also 0. Wonderful. I picked something else that was also 0. I kind of had a feeling, right? Because 7 times... Oops. Let's pick something else. Let's pick 18. So I don't want to get to this yet. So we're almost there, but let's not do it. So this gives us 59 mod 7, or no, I mean 60 mod 7, which will give us, or I'm sorry, yeah, 59 mod 7, which will give us 3. Okay, and so now we have to stick this into the third slot. So we go 0, 1, 2, 3, so we put this in slot 3. And that's what we do. Yeah. So let's pick another one. Let's try 5. And 5 is going to give us Robert. And so 3 times 5 plus 5 is equal to 20. Mod 7 is equal to 6. Right? So basically what we're going to do here is stick this in slot 6. So we go 0, 1, 2, 3, 4, 5, 6. Like that. Okay. Let's do one more. What's a good one? If we do 7, and then sure, I guess we'll do Alan, even though that's yeah. So then what we're going to do here is we're going to say 3 times 7, which of course is 21, plus 5. Mod 7 is actually equal to 5. And so what we can do here is we insert like so. And so now I'll put it down. I'll put this up a little bit, and I'll put this down a little bit. That way their parentheses aren't hitting each other. Okay. So does everyone see what I'm doing, right? So the question is not why yet. The question is, does everyone understand what I'm doing right now? And the answer should hopefully be, basically I'm just taking whatever number you feed me, and I am multiplying it by 3, adding 5, and modding by 7. And you see that that's kind of jumbling everything up, but it's putting things in the hash table, so that's fine. Okay, so so now I'm going to assume that everyone does. All right. So now let's discuss what the heck, like why, right? Why are we doing this? Right? And so the goal here is to have O of 1 insertions and O of 1 search. So you notice that a hash table, at least this hash table, if I ever say find the element, right? Find the element that corresponds with 18, you would take 3 times 18 mod 5 plus 5 mod 7. You would calculate its value. You would say spot 3. So then you go 0, 1, 2, 3. Actually, you don't go 0, 1, 2, 3. What you do is you just access the underlying array at the 3rd spot, right? And so searching and inserting are both O of 1 operations, right? So because, and so we're going to assume that hashing is an O of 1 operation and array access is O of 1. And so basically what we have is an O of 1 plus O of 1 operation equals O of 1, right? That's the general gist of why we're doing this. And you see why you could possibly want that, right? Because this is actually better searches. This gives us better search and insert times than even a binary search tree, red-black tree. It doesn't matter, right, how well you balance a BST. The search time is O of log n, right? But here it's O of 1, right? So it's O of 1 for a hash table. And so a hash table is definitely a much simpler data structure than a binary search tree. It's a much simpler structure than a red-black tree. It's a much simpler structure than a lot of objects, right? The only thing that's complicated, right, about this structure is the complication of the hash function. But here's the secret about the hash function. At least in 341, you're usually given the hash function. Okay? So, now, here are some requirements that the hash function has. Basically, in order to get the thing to be like this, we have to make some assumptions, right? So in order to be O of 1, we need to assume that that no two objects match to the same value, or this happens relatively rarely. Okay, and so it's possible that two things can collide, and so that's what I got when I tried to do 17. So let me discuss what happens. So there's a number of different options for what's called a hash collision. So now let's discuss hash collisions. So remember, if we try to insert something like 17 using our old hash function, and let's call this Julia, then our old hash function said, what did the old hash function say? It said 3 times 17 plus 5 is also equal to 0 mod 7, right? I guess for... why would we care more about same values over same keys? We actually care more about the same key, right? Because or the same hash to the same key. So let me show you what happens. So this is 0 mod 7, and so what we need to do here is this. This is what we need to do, right? So if two keys produce the same hash value, then this is called a collision, right? And in this case, Eric and Julia collide in, well, we'll call it like slot 0 of the array. So in principle, this is bad, right? And why is this bad? right? So why is it bad? It's bad mainly because, what do we do? Do we overwrite Eric? 3, Eric? No. We don't want to overwrite me. Can we save 2 things in the same slot? Generally not, but sorta, right? So, well, yeah, you'll see for project, for project 4, at least from what I've seen, we actually have a hash table of array-based heaps. So you have, so basically you'll implement a hash table, which is going to be hopefully fairly easy, and you'll implement an array-based heap. So it's basically project 4 is one of these structures, but let's get back to hash collisions for just a second. Yes, so the function is 3n plus 5, and so let me just talk about the different ways. So there's 2 different processes that they usually describe. So there's either open addressing, and then there's closed addressing. So let me talk about closed addressing first, because actually I like it, and I haven't seen it on a data structures project in many a year. And I actually think that, honestly, this is what I would make people do, because it's far less common in practice. And so basically, in practice, what closed addressing is, and usually it's described as you stick a linked list onto each array slot. So array slots are no longer, just like a, key value pair. They're now a linked list of pairs, right? And so that's how it works. So let me show you how closed addressing would work in this instance, right? So let's say that we do closed addressing here. So what you would do is, instead of, this is not possible. So what you would do is you would say, okay, cool. What I'm going to do is I am going to, like, my head node is here. I'm going to create a new node. Let's move Julia up in the Z order. And then let's draw an arrow. Right? And so nope. There we go. Okay, so this is how you would do it. And then let's insert another element. So what's another element that hashes to 0? I guess it has to hash to 2. So let's think of something that hashes to 2 when you multiply it by 3. So if we put 6 in there, no, it has to be 2 mod 7. So 5, 7, what about 9? 9 times 3 is 27. Mod 7 is -1. Okay, I'll just experiment around a little bit. So what is this 51 times 3 plus 5 mod 7? So that's 4. 3 plus 5 mod 7, that's 1. What is the multiplicative inverse of 3 mod 7? So 3 times 4 is 3 times 2 is -1. So 2 times 6 is 12. Mod 7 is 5. So basically, okay, I got it. So basically 5 times 3 is equal to 1 mod 7 is what I'm saying. And then, so we can actually calculate this here. So if we want to get something to be equal to 0 mod 7, it's equal to, and we have the equation 3x plus 5, then actually what we need is 2 mod 7 to be equal to 3x. And so we need, what did I say the multiplicative inverse was? Oh, it's 5, obviously. So yeah, 10, so 3 mod 7 is equal to x. So, we could just, let's insert 10. So inserting 10, 10 times 3 is 30, plus 5 is 35, mod 7 is 0. Good. I don't know if that took way too much thought. I don't know if that was obvious. Maybe I'm just not firing on all cylinders right now. So basically, if you're going to insert 10 again, then you stick it on here, and then you do something like this. Now, what is the problem with the closed addressing system, right? So this is closed, and so let's insert one that matches with ATIA. So this is 0, 1, 2, 3. So basically we need something that matches with 3. So if x is equal to if x is equal to, we want it to be 3 mod 7, so we want to solve this equation again. We want to solve it when we have 3 here, and so we want to say 3 mod 7 is 3x plus 5, so this will be minus 2, which is 5 mod 7 is equal to 3x. We multiply by 5 on both sides, so 25 mod 7 is 4, so we want it to be 4 mod 7. So I guess actually 11 is a good value. Oh, obviously, because if 10 is, then 11 maps to 3 more than that. Okay, okay. So if we insert 11, then 11 is going to insert here. Let me put a thing in here, and let me move this down. There we go. So this is called closed addressing, right? Now, what's the problem with closed addressing? So the problem with closed addressing is, do we still have O of 1 search times? So for insert, we can always insert at the head. So instead of inserting rich as the last element, you can always insert it as the first element and push the other ones down. So you can reclaim O of 1 insert. But what about search? The answer is not really. Not really for search. Search can actually, it's basically like O of n divided by t, where t is the table size, right? And so this is not good. On the other hand, the thing is that if n is bigger than the table size, then basically we needed a bigger hash table. And the reason why I say that is because there's something called the load factor in a hash table. The load factor is defined as the basically number of filled slots divided by the size of the table. Okay? And so, like in this case, the load factor is what? Like 1, 2, 3, 4 divided by 7, or technically you could actually, it could even be the number of elements. So the load factor here is a little bit hard to compute because it could either be the number of filled slots or it could be the total number of elements. If it's a total number of elements, then you're approaching 1 for a load factor. And so actually closed addressing would give you a way to give you... yeah, exactly. So yeah, you're going to have some issues when you get up close to the table size. It's possible. The worst case scenario in this case is if you keep inserting elements and they keep getting the same hash value, right? So if you got a linked list like this and just pretend like there's nothing else in the table, all there is in the table is basically this linked list, right? Then the problem is that actually this isn't a hash table anymore. What this really is, in terms of your actual like experimental data structure, is a linked list, right? And so that's the problem, is that you're now dealing with linked list runtimes, which are like O of n type runtimes. So the worst case scenario O of n if everything hashes to the same value. So basically the moral of the story here is that you have to make sure that your hash value function distributes elements kind of evenly, right? Or as evenly as possible. And this leads to something called a hash attack. So if the user knows about what exact hash function is being used, they can construct an attack, which means inserting elements that are all the same hash key value, right? Because then they'll all go into the same slot of the array. Okay. So, as it turns out, this is one way to do closed addressing. This is kind of the standard way. Can you improve, right, closed addressing? Can you make it better? And the answer is yes, you can make it better. You could make instead of having a linked list here, right, we could pick any other data structure to stick here. So technically, instead of having a linked list here, you could actually choose. So for closed addressing, you could improve closed addressing by, instead of using a linked list as your collision resolution data structure, you can use maybe a BST or even an AVL tree or red-black tree, right? If you use like a red-black tree, you guarantee yourself log n operations, right, within each slot. And so it kind of, the worst case scenario would then, instead of being O of n, it would be, you could in fact, right? So I'll show you, so that's basically the second part of it. Now let's talk about open addressing, which is what we're actually going to do for the project. So so this is closed addressing. Closed addressing, what it really means is use a secondary data structure to resolve hash collisions. Right? So now let's talk about open addressing. If a particular slot is filled, try a different slot. And so let me explain to you how we do this. So let's start with our original hash table. And now we're going to insert these elements again. But now we're going to use open addressing, which I haven't really told you or defined or anything, but I'm going to do it anyway. So let me show you what open addressing does. So open addressing says, Okay. And so there's actually there's a bunch of different ways to do open addressing. So let me show you the one that's called linear probing. Linear probing just means keep adding 1 until you find an open slot or the table is full. Okay. So for instance, Julia, remember Julia hashed to 0 and Archie hashed to 0. Rich hashed to here. So what you're going to do is when you try to insert Julia, you're going to insert Julia here instead of here. And so the thing is that that's resolving the hash collision by just sticking it in the next slot. And then in order to search for it, right, you have to keep going while the keys are still correct, right? So basically, let me show you what that means, is like, let's insert Archie now. So Archie's going to go here. And so basically, the reason why it goes there is because it tries to insert here. It can't because there's something in this slot. So then it tries to insert here. And it can't because there's something in this slot. So then it adds the offset of 2. And then it goes into the offset 2 slot. And then let's insert Rich. So Rich goes here. And so then Rich is going to go, instead of here, because there's a collision, it's going to go here. And so that is how linear probing works. So basically, linear probing, you just keep inserting, you keep going to the next element until you find something else. So now if we insert anything, basically, if we insert 31 Sam, right? So 3 times 31 is 93, plus 5 is 98 mod 7. So 98 mod 7 is 0 again. Okay, I'm an excellent hash attacker, but it doesn't matter. So 31 Sam is going to map to 0. So what happens is here it says, okay, I'm going to try to insert here. I can't. And then it goes to here and it says, I still can't. Back to the start. And so now what happens is this one just gets rejected. And why does it get rejected? The array, and also known as the hash table, is totally full, right? There's no space. So yes, this does cause some problems. It's not perfect, but this is how you're going to do it for your project. So, yep, okay. What if we didn't insert Rich, and what if we did insert Sam? So let me show you what happens if we do this. Actually, let's just copy paste this table. So basically, if we take out Rich, and then we try to insert Sam, so Sam goes into here, it doesn't go in, and so then, whoops. So then it tries to go here, it doesn't go in here, and then it looks at this spot, and it says, hey, wait, I have a different key to this guy, but it doesn't care, it jumps past it, and inserts itself here. Yeah, basically, at this point, so you're right, because, and so the moral of the story here is, when you use, you've got to keep the load factor, remember, which is the number of elements divided by the size of table. You have to keep it less than 1, and not just like 0.9, right? You want to keep it at least at like 0.5 or less. So you want to basically have a hash table which most of the time is mostly empty. And the reason why you want this is because if you start filling it up, then you start getting array behavior, right? You start getting array behavior, and that's not good because you don't want the thing to behave like an array. You want the thing to behave like, well, I mean, I'm sorry, you don't want the thing to behave like a linked list, and that's kind of what this is, right? because this next object is here, the next object is here, and the next object actually jumps over this one and goes to here, but you have to search this one anyway, so it's really like a big linked list now when you're searching for anything. And so basically, this is as inefficient as possible. And so basically, you want a lot of open space so that in case that you have to go searching for something, then you know that you're not going to have to search the entire array for that value. It is a bit chaotic. Let's do let's do another example where let's make a better hash function. And by better hash function, I mean let's take the absolute simplest hash function in existence. And first, let's compute what's the size of this thing. I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's 11, 12, 13. Okay, so this table is of size 13. The hash function is going to be x. It's going to be the identity function mod 13. Okay? And you might think to yourself, wait, crap, that's a terrible hash function. But whatever, it's simple. And it's good because now I can easily induce hash collisions. So let's insert some elements. Let's insert 1, 3, 5, 17, 21, 33, 85, 20, let's say 26, 36, I guess, 26, 25, and 12. Let's insert all of these elements into the hash table. So basically 1 goes into slot 1. And remember that this starts at slot 0, so this is slot 1, 2, 3. Here's 5. So now 17 mod 13 is 4, so we put this in slot 4. 33 mod 13, so that's negative 3, so minus 1, minus 2, minus 3. So I think that goes here. 85 mod 13. I'm just going to cheat and use a calculator. Right? Because, am I stupid? Is there an obvious thing? 7? I don't know. Maybe it was obvious, maybe it's not. I guess if I ask the question, is it obvious? The answer is, it might not be obvious. 26 is actually 0, right? 26 is 0. 25 is up here. And then we get to 12, right? So now when we insert 12, here's our first hash collision. So our first hash collision says, let's try to insert here. We can't. Go to the next element. We can't. We can't go to the next element. We can't. Here we can. And so now the problem is that, as I say, when you search, right, for the element 12, you can't just hash it. You have to hash it and then loop around until you find an empty space. Okay? And so let me insert 2 now and show you what happens. So if we insert 2, what happens? So 2 is going to do something like this. It's going to go in here. It's going to say 2, 2, 2, 2, 2, 2, 2, here. That's the first open spot, so that's where it goes. And so you see that this is kind of bad behavior, but it's kind of in a simple example, and also our load factor is way bigger than a half now, so, or it's at least slightly bigger than a half. So, and what's 10 out of 13? 7.75. So you see that with a hash factor of about 0.75, you're going to start to get bad behavior using linear probing. So what if I delete 12? Right? What happens if I delete 12? And the answer to that is, well, if I delete 12 out of the hash table, I can't just do that, right? Because now, if I tried to search for 2, I would search for 2, it would pop up, oh, it would pop up here. And then I would say, well, 2's not in the hash table because this spot's empty. But the reason why this spot's empty is because it was occupied by a different value that was then deleted. So actually what I need to do is, if I delete 12, I also need to search all the values here and see if any of them match this key. Is like, does 3 match this key? No. Does 17 match this key? No. Does 5 match this key? No. Does 2 match the key? Yes. Shift it back. And then again, if I had a 15 here, 15 would also match this hash key. So then what I have to do is keep searching. 85, do you match the hash key? No. 15, do you match the hash key? Yes. Shift you back. Shift you back. Come on. Go back. There we go. Shift you back. So basically 2 and 15 have to shift back. In order to keep the hash collisions working. So then if you delete 2, for instance, if you delete 2 instead of deleting, so now if you delete 2, you also have to search, and then you find 15, which mod 13 is 2, and then you have to shift this one back. So as you delete them, you have to shift the ones that have the right values back. So it's a lot of work. Basically, in order to guarantee O of 1 times, we have to assume that the hash function distributes elements evenly, no attacks are done, and the load factor is like small. Like, right? We want the load factor to be small, because if the load factor gets big, like if it gets close to 0.5, if it gets to close to 0.75, if it gets close to 1, then what you're going to see is that this thing is just going to behave like a weird, funky linked list, and it's going to have O of n runtimes. So the secret actually is, we can ensure a small load factor by resizing the array whenever we get above a critical load factor. So instead of just being like, well, there's nothing we can do, we're just about to fill up the hash table, things are going to go badly, we can just double the size of the hash table. And that will guarantee that we always stay below some critical load factor. Because as soon as we get close to that load factor, you increase the size of the table by 2, and then what it does is it doubles the total number, the load factor gets divided by 2, and so that's how we do it. So that's open addressing, and this is what you're going to actually use for the project. The good news for the project is you are not actually going to have to delete in the project. So, but yeah, so this is what you would do if you did open addressing. So let's do a different method of open addressing. This is called linear probing, right? This whole thing was linear probing. And you see why it's linear, right? Because the offset each time is just 1. You just add 1, add 1, add 1, add 1. So what happens if you do what's called quadratic probing? So let's do open addressing with quadratic probing. So with linear probing and quadratic probing, it's about the same, except whenever there's a hash collision, instead of just going hash of x plus offset, what you do, this is linear probing, and technically you would still have to take hash of x plus offset mod table size. So that's linear probing. For quadratic probing, what you do is you do hash of x plus offset squared, sure, mod table size. This is quadratic. And so let's do a simple example of this. Let's create some boxes. Let's create 10 boxes. That way, we're going to use the hash function h of x equals x. So this is 2, 4, 6, 8, and then we're going to do 10. So now hash attacks are mega simple. So let's insert the element 3. So the element 3 goes in here. Yep. And so now we're going to insert something that hash attacks it. So 33 also has the same value. And so 33 mod 10 is equal to 3. So it's going to go into slot 3. And remember that I'm using the hash function. So normally this is very bad. You don't want to be doing this because this leaves you open to hash attacks. But in the case of education, we don't care, right? This is like for educational purposes. So it would try to go in here. So then the offset is 1, so it would go into here. Okay, so that's fine. That's just like linear probing, right? So this part was just like linear. So that's, that's fine. But now let's say that we try to insert, say, 53. So what happens this time? Right? So what happens this time is that the offset is 0, but there's a collision. The offset is 1 squared, which is 1. There's a collision. So now the offset is 2 squared, which is 4. So we go 1, 2, 3, 4, and we stick 53 in here. Okay? All right, cool. Let's do it again. Let's say that now we want to do... Okay. Come on, let me edit. Let's do 73, right? So if 73 tries to insert, we would get offset of 1, offset of 4, and then the next offset is 9, right? So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's that. So now let's insert 23. Okay, so 23 mod, so remember that the offset is now going to be, so we're going to insert with an offset of 1 squared, and then this is the offset of 2 squared, this is the offset of 3 squared, and now basically 16, right, is the next one, 4 squared. So we're going to start here, and we're going to do 4 squared, we're going to get 16, so we're going to go 1, 2, 3, 4, 5, 6. Okay. And finally, let's insert 13. And now we're going to see something else, I think, right? So what is the next one after 16? 25. So, okay, no, not yet, almost. So we go 0, 1, 2, 3, 4, 5. And so basically this was, let's just put in the offsets here, right? So this is an offset of 1 squared. This is the offset of 2 squared, which is 4. So basically I'll just draw in 4 here. This is the offset of 9, which is 3 squared. This is the offset of 16. This is the offset of 25. And now you see that the next square is going to be something else, right? The next square is going to be... There we go. The next square is going to be 36. But 36 is bad, right? Why is 36 bad? Well, it's not, bad all the time, but with a hash table of size 10, think about it this way. 16 mod 10 is equal to 6. 36 mod 10 is equal to 6. Ah, crap. Right? Because what does this mean? What does this tell us? What this tells us is that we're going to try to insert the element at... And watch what happens. So let's insert another element, which is 3. So let's say 43 is going to be the element that we're going to insert. So let's insert 43. And so now what we're going to do is we're going to say, okay, stick it in slot 0, collision. Stick it in slot 1, collision. Slot offset 4, collision. Slot offset 3, right? Which 3 squared is 9, collision. 16, collision. 25, collision. 36, same as 16, collision again. What about 49? That's the next one, right? Or no, what am I talking about? So yeah, no, 6 squared is 36, 7 squared is 49, collision. 8. 8 squared is 64, collision. 9 squared, 81, collision. 100 squared, right? Or 10 squared, 100, collision. 11 squared, 121, collision. 12 squared, 144, collision. 13 squared, 169, collision. I think I've done it long enough. So we see that 43 is just done. It can't go in. And the reason why it can't go in is not because the hash table is full, but it's actually a number theory reason. It's that the quadratic residues mod the table size can only have certain values. And so for 10, the values are 1, 4, 5, 6, and 9. If you square anything in the universe, mod it by 10, you'll get a number, I guess 0 technically, in that list. There are no squares, which are 7 mod 10. So x squared is equal to 7 mod 10 has no solutions. Same thing with x squared is equal to 8 mod 10, or x squared is equal to 3 mod 10, or x squared is equal to 2 mod 10, etc. Right? So these are like, I guess actually we call these non-residues mod 10. And so you see that quadratic probing is kind of a gimmick in a way, right? I mean, there's good. So one thing that quadratic probing does do for you is it pushes elements further and further away from your original starting element. So what it does is it gives things a chance to be more evenly distributed around the hash table. On the other hand, it runs into this number theoretic problem, which is basically that, like, when you do a mod by the size of the table, there are only a certain number of solutions, and then there's a bunch of non-solutions. So 43 is just out of luck, right? The table isn't full, but the residues aren't going to help us anymore. So that's the moral of the story with quadratic hashing. Okay? Now, I should say quadratic probing with open addressing, right? So that's the moral of this story. And there's a number of ways. So basically now I've taught you linear probing, and I've taught you quadratic probing, and I've taught you closed addressing, which is using some other secondary data structure. So that's basically the moral of this story. So there's another way to resolve. There's yet another way to resolve with open addressing. Whoa, I didn't even know you could do this. So let me just mention the last way, and we'll discuss this next time. The secondary hashing. So I think someone actually suggested this idea first, and this is like the most complex open addressing idea, which is you have a hash function, you have hash 1, and you have hash 2, right? And so basically what you do is you say, well, if hash 1 collides, you can't just compute hash 2. You actually have to compute hash 1 plus hash 2. right? So hash 2 is the offset. So if there's not a collision, you use hash 1 of x. And if there is a collision, you use hash 1 of x plus hash 2 of x. And so now you see the issue with this secondary hashing is that this will only resolve a single collision. So technically what you actually need to do, and so sometimes what you do is, if there's another collision, you'll just use like 2 times hash 2, and then you'll use 3 times hash 2, or you'll use 4 times hash 2, etc. But technically, you could even have like hash 1, hash 2, hash 3, hash 4, hash 5, all the way down to hash infinity, right? Basically, you could have an infinite collection of hash functions. And so if there's one collision, if there is a collision, then you compute hash 1 of x. Or, I'm sorry, if there's no collision. If there is one collision, you can compute hash 1 of x plus hash 2 of x. 2 collisions, hash 1 of x plus hash 2 of x plus hash 3 of x, etc. So each one of these different methods tends to present a slight issue. So here's the question for you, and I'll cover this next time. The question is why do I have to add these, right? Like, why do I have to add this? You know, why can't I just hash 1, then hash 2, then maybe hash 3, or whatever, right? Why can't I do that? And the secret, I'll give you like a little hint. The theory is that if you actually go searching for the element and the element exists, you're going to find it at hash 1. And then the thing is that if you do hash 2 first, the question is, did hash 1 produce the hash 2 value, or did hash 2 produce the hash 2 value? And so that's the kind of thing that you have to think about. If hash 1 produced the hash, like if hash 1 and hash 2 both produce y, I guess the tricky reason is, like, think about what happens when hash 1 of x, or let's say, yeah, hash 1 of w is equal to y, and hash 2 of v is equal to y. So they're two different elements, maybe, and they produce the same hash value, but they produce the same hash value in the two different hash functions, right? So this would mean that you would try to insert this one at y, and then if there is a collision, say that this one already had something that had a hash value of y, or hash 1 value that was different, you would try to insert this at y, and then the question is which one of these, you know, is the one that you're looking for. And so that's the hint, is like there are issues that come up when both of the hash functions produce the same value. It would be hard to tell which one had produced the result. So anyway, that is basically hash tables in a nutshell. You have learned just about everything about hash tables except for how to make good hash functions. I'll probably discuss that next time and do some live coding. So you know, next time we'll do some live coding. I'll do some quadratic probing, maybe secondary hashing, maybe closed addressing, and then we'll maybe do some hash table races, right, to which is best. So the last thing I want to say before I let you all go, and I know that I started class and I'm ending class a bit late, is that all of this stuff you've seen before. If you took 201 with me and you had dictionaries, Dictionaries are hash tables in Python. In Java, they're called hash maps. In Ruby, they're just called hash. So basically, there are hash tables in a lot of different languages. I think even C++ now has like an STL hash implementation, perhaps. So, but you're going to be implementing your own hash table. So that is that. Okay. Hopefully today's lecture wasn't too boring, since all we did today was like stick stuff in arrays, right? So that's kind of all we did, right? But on the other hand, you know, that's all hash tables are. So we can talk more about load factor, more about what like other, Python and other STL things track their load factors, and they'll expand the table whenever the load factor gets too close to whatever some critical load factor is. Most hash tables do not let their load factors get anywhere close to 1. And you see exactly why in these examples, right? If you start letting it get close to 1, you get linked list O of n type behavior. If you keep the thing sparse, mostly empty, then you get good O of 1 behavior. And it really depends on like how many elements you expect to see that are like hash collisions. And that really hurts you. So hash collisions really hurt you. And so obviously that is the whole moral of this lecture. Okay. So I think I will call it a day. I basically did the entire lecture in this Inkscape program. I intended to do some live coding, but you know what? It's fine. Today's lecture was entirely explanation. Hopefully people understood what I was talking about. If you don't understand secondary hashing yet, that's okay. I haven't really taught it. We'll talk about it next time. Hopefully you do understand linear, linear probing, quadratic probing, closed addressing. So closed addressing, most of the time they say it uses a linked list, but actually if you think about it, there's no rule that it says it has to be a linked list. It just, most people talk about it being a linked list. You could use any data structure as a secondary data structure. So free your minds about that. Don't think it just has to be a linked list, because a lot of people say, oh, it has to give the worst possible performance, but it doesn't actually. Okay, that's all for today. I'm assuming that you're going to go and work on your projects now. Okay, let me see how to turn this thing off. Nope, that's not how to do it. That's how to do it.